All right, so here's the problem in question, right? So we're talking about the potential energy of this system. And uh, it's not an easy problem. You have to kind of get into the weeds a little bit of how this works. But the correct answer, if it didn't show you at the end, is negative 5gm squared over r. And you might be thinking, well, good God, where does that come from? But so let's try and follow my reasoning here. So if something's close to the surface of the Earth, we know that it's mgh. But we're not talking about three balls near the surface of the Earth. We're talking about three masses that have come in from infinity, kind of thing. So hopefully you can see this. So if I have two masses separated by distance d, the potential energy is kind of equal to the work, right? Work and potential energy, or work is a change in energy. So potential energy is more or less equal to the work done. Work is force times distance when that's parallel to each other. But keep in mind that work is also a scalar. So if I use the universal gravitational formula, Newton's formula for universal gravitation, gmm over r squared, and if these two masses were the same and the distance was d, I'd get gmm squared d over r squared. But if the distance between the two is d, then d and r cancels, right? So I get this formula. The gravitational potential energy is going to be equal to big G times the masses squared divided by the distance. Okay, so with that in mind, I'm just kind of restating here between M and M. So if I look at the picture, between these two guys, because this is a system now, between those two guys, direction doesn't matter because we're talking energy and work. So between those two guys, I have gm squared over r. And then between m and 2m, so over here I have between m and 2m, and on this side also I have between m and 2m. I'm now going to do the same thing. Potential energy is force times distance, except I have a single mass and a double mass, so that's going to give me 2gm squared over r. And I have that condition twice, so 2 and 2, 4, plus down here, 1 is 5. So that's where the 5 comes from. But now you might be thinking, where the hell does the negative come from? And I mentioned it once in class, but I don't think we've really had any problems that have dealt with this. So part of the reason I'm making the video now. So what the hell did I do here? So here I'm just showing that like the potential due to this side is 2gm over r, and the potential due to this side, 2gm squared over r, right? 2gm squared and squared over r. So that's where I get my 5 from, right? 1, 2, 3, 4, 5 of the system. Yeah, so I'm just kind of showing this again. So I started thinking about this, like how can I explain the negative sign? So if you think about gravitational potential energy close to the surface of the Earth, right? As you go higher up, mgh gets greater, so you would have potential energy versus distance would give you this nice straight line, and that nice straight line would be mg, or the force of gravity, right? So hopefully that makes sense. If you're talking about out from space, right, you're like, okay, well, we've got this formula, PE equals gm squared over r. So P, G's a constant, and if the mass of the planet and the mass of the object are constant, then PE is proportional to 1 over r. So the graph would look like this. Okay, that makes sense to me, but everything is still positive. So, okay, this is a straight line because we're saying that the gravitational field strength isn't changing, but you get far enough away where the gravitational field strength is changing, and you say, okay, now it's going to look like this. Fine. But where does the negative come from? So, in thinking about this, I said, well, okay, let's see. If I'm close to the planet, I have a little bit of PE, and I have a lot of KE, right? Conservation of energy. So if the dotted line was the total amount of energy in an object that was allowed to move relative to a planet that doesn't move, I was thinking, okay, he'd have a lot of PE. A lot of PE close? Well, definitely, if you got really far away, right, he'd have almost no kinetic energy. And as you got close, he'd have a lot of kinetic energy. So I started thinking, well, okay, if energy's conserved, that means that far away, he'd have more potential energy, and close, he'd have less potential energy. But kind of doesn't make sense, right? I'm not getting that 1/r relationship here. So I think the key lies in, if you were to take the mass away from the planet to infinity, right? If you were to go out to infinity, cover up my backdrop here. Out at infinity, there'd be no energy. It wouldn't have potential or kinetic. So if I had a planet like Earth, and I've got some tennis ball that's way beyond the solar system, right? That system between the Earth and the tennis ball, if it was truly at infinity, would be zero. So the total energy at infinity has to be zero. KE plus PE equals zero at infinity. And as I get closer to Earth, as the distance gets less, this horizontal axis is distance, the kinetic energy is going to go up, and it's going to go up as a square. So without explaining that, if you just take that to be true, if the kinetic energy goes up as a square like this, and energy has to be conserved, then PE also increases as we get closer to Earth, but it has to increase as a negative, because at any given point, at any given distance, the total energy has to be zero when compared to infinity. So, I don't know of an easier way of stating it other than this here at the bottom, right? This is the usual way of explaining it. So in this particular problem, three spheres with masses indicated above, m, m, and 2m, are initially far away from each other. So that's kind of the idea here, is I'm bringing them in from far away. So you can think of it as the potential energy is equal to the work done in bringing those spheres closer to each other. But three spheres with masses indicated above are initially far away from each other, and the gravitational potential energy of this three-sphere system is zero. So that's this condition. They're far enough away that it starts out at zero. Because it starts out at zero and the spheres are then brought together, that's why we're getting the negative sign. It doesn't really sit well with me, but yeah, that's kind of how we explain it. So the spheres are brought together until each sphere is a distance r from the other two, as shown above. What is the new gravitational potential energy of this three-sphere system? Yeah, so I'm kind of glad this one popped up, because it was something we really didn't cover much in class. I'm kind of searching around to see if I can just get a little more information and talk about it in class. I was looking here on this Khan Academy, and this is what they talk about when they talk about a gravity well. So if we have Pluto and we have Pluto's moon, you can see this same kind of negative curve as you get close to the planet here, I guess. But in any event, yeah, so that's kind of my fast explanation of why that one is what it is. Not a huge part of the AP, but to be able to know that potential energy can be expressed as GM over R squared, I'm glad this problem came up.